Hello, so we're going to be looking at the lab you're going to be doing this week. And we just simply call this the Gas Laws Lab because that's what we're doing. We're doing the ideal gas law. And we're going to explore a certain type of reaction with it. And this type of reaction, of course, you should recognize it immediately as a displacement, or the most basic of redox reactions. So what we're going to actually be doing is taking a metal, and that metal is either going to be magnesium or calcium. So as I do this demo, I'm going to be writing it as strontium, because if you look further on down the periodic table in the alkaline earth metals, you'll see that strontium is also there. So we're going to use strontium as an example. So you've already done this before. You used magnesium and you added hydrochloric acid to it. And when you added, or the other way around, depending on your choice, we ended up with strontium chloride, which was dissolved, of course, so we didn't see it. And we also had hydrogen gas that effervesced right out of the solution. So what you're going to be doing is figuring out the stoichiometry of this particular thing. Now, of course, it would take us 2 seconds and we would say, oh, I know what this is. We need a 2 here. And yes, that's true. So we know we're looking for a 2 and that this would be a 1 and a 1 and a 1. We're going to be using the gas laws, the ideal gas law, and this experiment to prove this to ourselves. So let's take a look at exactly what we're going to be doing. Now this is kind of a fun and awkward setup, but that's okay. The first thing we're going to be doing is adding to this flask a known quantity, 25 milliliters, of a known standardized HCl solution. All right? And we're going to be then adding to it a known quantity, like analytical balance known quantity, so being picky here, 4 sig figs, of strontium. Now we know strontium, I'm going to rewrite that equation from above. Strontium plus the hydrochloric acid will give us hydrogen gas and strontium chloride, which will stay dissolved in the water that we had from the aqueous hydrochloric acid. So what is happening in here is exactly this reaction. Now we put in an excess of HCl, so the strontium is going to be our limiting reactant. What we're going to do, of course, is make gas. Now, in our lab, we don't have a particularly good way of capturing that gas to find the volume, so we can use our ideal gas law. We're going to be looking for N in all of this, of course, because N is the number of moles. So we don't have a good way of capturing this gas. So instead, our setup allows us to have this gas pass through this tube into what's called a Florence flask. And this flask is already sealed. All of these things are sealed perfectly except for this. Into this flask is going to be pushed this gas. And what's going to happen is this gas, the hydrogen gas itself, is going to exert a pressure on the water. And the water's way of escaping, because there's no more room in that Florence flask, the water's way of escaping is up this tube. And it will then empty into this reservoir flask. So to run it through again, you're going to have excess acid, known amount, known number of moles. You're going to add a known number of moles of strontium, or in your case, magnesium or calcium. The gas generated is going to go through this tube and into the Florence flask, where it's going to exert a pressure on the water. The water is going to come out, and a certain volume of water is going to be deposited into the reservoir flask. So that's the procedure. I'm not going to be telling you all the details. That's something that Mr. Proetta will tell you in the actual lab video that he's doing. But I want to get across to you what's actually going on. Now, we know this is HCl, and eventually will be also the strontium chloride in here. The gas is moving. Now, hydrogen gas does not dissolve in water. It does not dissolve in water. Therefore, for every molecule of hydrogen gas that goes into the Florence flask, the same amount of water will come out. Okay, this will be 1-to-1. 1-to-1 hydrogen to water. Okay? And this is important because we need to know, remember, we're trying to solve for N here. And we need to know a certain number of things. We need to know R. Well, we know R. 0.08206. Let me write it down here where I have room. We have R equaling 0.08206 liter atmospheres per mole K. So we have an R. Temperature. Well, we have a temperature. This water will be at room temperature. It's left out for a long time to make sure it's at room temperature. And at room temperature, let's say it's maybe 23.25 degrees Celsius. We'll convert that to Kelvin, and then we know the temperature. So what we have left is the pressure and the volume. And the volume of hydrogen gas we can get from the volume of water that's displaced. Now, there's an issue. If we use the beaker to measure the water, that's not anywhere near accurate enough. If we use, I don't know, a graduated cylinder to measure the water, even that's not accurate enough, because sometimes we make over 100, we should be making over 100 milliliters of water. So this would have to go into a 250 graduated cylinder, and actually we don't have enough of those for all of you, and it doesn't have enough sig figs. We have 4 sig figs from our mass. We want to have 4 sig figs from our water. That's what we want. So we're going to, I'm going to erase a little bit of stuff here so I have some room. Since we want 4 significant figures for the water, what we're going to end up doing is massing the water on a top loader. A top loading balance. That way we will definitely get 4 sig figs. Okay? So we're massing it on the top loader. But we want to have it be a volume, don't we? We want to have it, let's see, in liters. So does anybody have an idea how we can get from mass in grams to liters? Right, we're going to have to use the density of water. Now we're going to have to use the density of water that's pretty accurate. Again, we want to keep 4 sig figs. This is the type of thing that scientists think of the whole time they're trying to run an experiment, is how careful I want to be, how many significant figures I want to have. So you don't just say 1 gram per milliliter and then convert it. We're going to be using a density chart. So the temperature at which all of this happens, we're going to use that chart to find the density of water. So let's say it's 0.9972 grams per 1 milliliter. And then, of course, we're going to have to convert that to liters. And we can do that very easily, right? 1 liter over 1,000 milliliters. And that'll give us our volume. 2 plenty of significant figures. So now we've got the volume. Finally, the pressure. Okay, so this is going to require some thinking about our gas laws that we've been doing recently. We know we have our temperature, we know we have our volume, we know we're looking for our N, we have our R because it's a constant, so pressure. Now, this was one thing that I mentioned in lecture, so I hope you were listening well, and I hope you read or watched the leftover video, so to speak. Because we're capturing gas over water. So this is a Dalton's law of partial pressure thing. Our pressure total is going to be equal to the pressure here in the Florence flask of some water, the vapor pressure, plus the pressure of the gas. Okay, that's not a big deal. We're looking for the pressure of hydrogen gas. We've got the volume of hydrogen gas, we've got R, which is a constant, we've got the temperature of the whole system, which is the temperature of the hydrogen gas. What we're going to need to find now is the vapor pressure of water. Okay, so we have a chart for that. So the chart for the density and the chart for the vapor pressure usually hang out on the front board. So we'll be able to find the vapor pressure from the chart of water, but we're looking for the pressure of hydrogen gas. I guess that means we need to know the total pressure, right? Pressure of hydrogen gas, after all, is going to be equal to the total pressure minus the vapor pressure of water, which we do know. Well, what we're going to be doing, and again, Mr. Proetta will walk you through this as we look at the setup and the actual experiment itself, but what you're going to find is that the P total, this whole apparatus, is set up so that the P total equals the barometric pressure, which means the pressure in the room. Okay? And that's something that you will be measuring at the beginning of the experiment. So you'll know the pressure of the room, you'll know the pressure of vapor pressure of water, you'll be able to find the pressure of hydrogen gas. So there we have it. We have everything we need to find the moles of hydrogen gas. Pressure we've got, volume we've got, R is a constant, and the temperature we've got. Remember, that has to be in Kelvin. So that is what we're doing for this. Our theory is that we have strontium, or some alkaline earth metal, reacting with HCl to produce hydrogen gas and the metal chloride. That hydrogen gas is what we're interested in. We're going to capture it in the Florence flask. An equivalent amount of water is going to be expelled, and then we're going to do lots of math. So from this N, we will be able to figure out our hydrogen gas coefficient. And we'll talk about how we're going to figure that out in just a second. Let's get ourselves a little more room. So that the data that you're going to have at the end of this is the mass of the strontium. And you're going to have the N of the hydrogen gas. But the other stoichiometric coefficient that we're going to be looking for is the N of the hydrochloric acid that you're adding. Okay? We need to know the coefficients for the whole thing. Right there. That's what we need to know. The coefficient for HCl. So, how are we going to find the moles of the hydrochloric acid? We used 25.00 milliliters, or 0.02500 liters of a standardized acid. So we know the liters, and we know the molarity, because it'll be written on the bottle, so that'll give us the number of moles of hydrochloric acid. Some of this acid gets used up, but some of it is left over or excess. Uh-oh. Well, so how are we going to figure out how much is excess? Because the used up amount is the stuff we want. We can titrate that leftover. So how we're going to find the moles of hydrochloric acid that were actually used in the reaction is by titrating the solution, and this is the solution that's in the Erlenmeyer flask, in that reaction flask. We're going to titrate that and find the number of moles of hydrochloric acid that were used. We find that, again, by the total that we calculate, given this, minus the number of moles that were excess, which we find from the titration, will give us the number of moles used in the reaction or consumed in the reaction. So all you're going to have to do is titrate that remaining hydrochloric acid with a standardized base, and you'll find that number of moles of excess hydrochloric acid. Now you've got the number of moles that you used of hydrochloric acid. You've got the number of moles of hydrogen gas. So we can put something in here and we can put something in here. We don't care about this guy. Uh-oh, we're missing this. I've got the mass of strontium. How can I get that? Use different letters. How can I get the number of moles of strontium from the mass? Exactly, using the molar mass. So you're going to have grams of strontium times the molar mass inversion of the molar mass, or divided by the molar mass. and that'll finally give us the last mole we need. Now, given that these all are fractions, you're going to do a ratio to finally find out what the complete equation is in terms of whole numbers. We'll talk through that and through all of these equations and calculations in the processing the data video.